Okay, good morning, forecast. So we are here to revise ions and ionic bonding. This is the second Zoom consult, okay, for the June holidays. So today we are revising ions and ionic bonding. So last lesson, we have revised what is atom. We have revised how do we deduce the number of protons, electrons, and neutrons in an atom from the periodic table. So last lesson, we talked about things like proton number, nucleon number. All right. So this lesson, we will focus solely on the ions and how ionic bonds work. All right. So at the end of today, you must be able to explain how and why ions form. You must also be able to explain the physical properties of ionic compounds. All right. So this can be found in your Chemistry 1 notes under your personal folder under class notes. So this is the second one, JH2. So ions and ionic bonding. So before we go on to the questions, we will go through a little bit of content first. So if you recall, last lesson, we have spoken about atoms and ions. So we spoke about something like potassium. Now the potassium atom has 19 electrons. All right, 19 electrons, how is it filled? How is the electronic configuration of a potassium atom? The first shell contains a maximum of 2 electrons, second shell 8, third shell also usually a maximum of 8, and finally, if you count properly, there must be 1 electron in the fourth shell. And that's why we say that potassium has 1 valence electron. So if we recall, valence means outermost. All right, so it has 1 electron in its outermost electron shell. Hence, potassium has 1 valence electron. And that's why potassium is from group 1 of the periodic table. Okay, so that's what we did last lesson. Now, this is obviously not stable. Okay, 2881 is not a stable electronic configuration. And this is because it does not have a fully filled outermost electron shell. So because it only has 1 electron in its fourth shell, the fourth shell is not fully filled. All right, so it is not stable as a result. Okay, so as a result of this, what will potassium do? We have already gone through this last lesson. Potassium will lose 1 valence electron. And after it loses 1 valence electron, it becomes 2, 8, 8. All right, it loses that 1 electron in the outermost electron shell. And as a result, you can see now potassium has 8 electrons in its outer shell. But this is no longer an atom, it's an ion. All right, and ions have charge. Unlike atoms, atoms do not have charge. Atoms do not have charge because the proton number is the same as the electron number. However, in an ion, because ions are formed by losing or gaining electrons, the number of electrons will no longer be the same as the protons. All right, so as you can see, potassium had 19 electrons, it lost 1. Therefore, now it has 18 electrons. At first, it had 19 electrons in the atom, but it lost 1 valence electron. Therefore, it only has 18 left. So in terms of electrons, 18. However, for the protons, protons do not change. The number of protons doesn't change because protons are not lost or gained. As a result, the potassium ion still has 19 protons. If you recall, protons are positively charged. So now you can see the number of electrons is less than the proton. So this is a positive ion because you have fewer electrons, fewer negative electrons than the positive protons. Therefore, this is a positive ion. And how positive is it? It's 1 plus. It's 1 plus because it only lost 1 valence electron. All right. Now, how would you phrase this as an answer? Let's say if the question asked you, explain how and why potassium atoms form ions. how and why potassium atoms form ions. How would you explain this? Well, first you need to explain the potassium atom has one valence electron, right? The potassium atom has one valence electron and does not have a fully filled outermost electron shell. Okay, you might want to add also that the potassium electronic configuration is 2881. Okay, so this explains why the atom is not stable, because it doesn't have a fully filled outer electron shell. Hence, the potassium atom loses one valence electron. So this is the how. The how is that it loses one valence electron. And when it loses that one valence electron, remember, lose electron means it becomes a positive ion. You lose one, therefore it's K plus. All right? So potassium forms K plus because it loses one valence electron. The K plus ion has stability because it has a fully filled outermost electron shell. And this is the why. All right, so you can include as 288. Okay. So just ensure you have taken this down. This explains how you are supposed to phrase your answer. Okay. So when it comes to drawing it out, I think last lesson we also drew it out. The potassium atom 2881. This is the atom, right? How do you draw the ion then? And the ion is just 288, so basically you draw 2, 8, 8. Remember, for ions, you have to square bracket, enclose them in a square bracket, and put the charge outside. So this is the ion. Right? So that's for potassium. Potassium started off as an atom, 2881, one valence electron. It's not stable, therefore it loses one valence electron to form the potassium ion, which is K plus. Okay, with a fully filled outermost electron shell. So this is a summary of potassium, how it forms an ion. All right. Now, do all atoms lose one valence electron? That's the question. Are all atoms like potassium? Do they always lose one valence electron? And the answer, of course, is no. Because not all elements have one valence electron. Not all elements have one electron in the outer electron shell. Take, for example, we can think of other elements from, say, group 2, group 3. Remember, the group number tells you how many valence electrons it has. So an element from group 3 will have 3 valence electrons. If it has 3 valence electrons, it cannot just lose one valence electron. So now we're going to look at another element like aluminium. Now, aluminium, if you look in the periodic table, has 13 protons, hence 13 electrons in its atom. All right. Atoms, protons, and electrons are in the same number. Therefore, aluminium has 13 protons and so also has 13 electrons. So how are the 13 going to be arranged into its electronic configurations? First shell 2, second shell 8, right? Because the first shell holds a maximum of 2, second shell holds a maximum of 8. However, there are 13 electrons. 2 plus 8 is only 10. So the last 3 electrons goes into the third electron shell. So it's quite obvious. Aluminium has 3 valence electrons. It's not stable because the outer shell, which is the third shell, only has 3 valence electrons. If it has 3 valence electrons, clearly it cannot just be losing 1 like potassium. It needs to lose 3. And that gives you 2, 8. As a result of that, now the outer electron shell is the second shell, which has 8 electrons in it. Therefore, the aluminium ion is now stable because it has a fully filled outermost electron shell, because the outermost shell is now the second shell in the ion. So it already has 8 electrons, which is fully filled. Now, what is the charge though? Is it still just 1 plus? Just now, potassium was 1 plus because it lost 1 valence electron. But this is 3 plus because it loses 3 valence electrons. So if you lose 1 valence electron, it's 1 plus. If you lose 2 valence electrons, it's 2 plus. If you lose 3 valence electrons, 3 plus. So let's quickly jot this down. If you lose 1 valence electron, it's 1 plus charge. Lose 2, 2 plus. Lose 3, 3 plus. And we can even relate this to the group. We already know group 1 has 1 valence electron. So all the group 1 elements, lithium, sodium, potassium, they all form 1 plus ions. Which elements will lose 2 electrons? They will lose 2 electrons if they have 2 valence electrons. So group 2. So beryllium, magnesium, calcium, strontium, barium. These are all the group 2 metals. So they lose 2 valence electrons to form ions with a 2 plus charge. All right. Finally, the ones that lose 3, group 3, like aluminium. Aluminium forms Al3 plus ions. Now, this is crucial. The reason why we're going through this slowly now is to jog your memory so that later on, when we were to write chemical formula, you are familiar with the charge. If you are not familiar with the charges, it's going to be very difficult to actually write chemical formula correctly. One of the major barriers towards writing equations is that your formula is not correct. If your formula is not correct, there is no point balancing the equation because you will not get any marks. The way to get marks for chemical equations is to ensure that your formula is correct to start with. And the formula is only correct if you got the charges correct. All right. So at this juncture, can we just check that you have copied down everything that is needed for aluminium and potassium? Okay. Once you are done copying down whatever is needed for aluminium and potassium and how they form their ions, please give me a thumbs up so that I know you're done. So as you have seen so far, potassium loses 1 valence electron to form K plus ions with a fully filled outermost electron shell. Aluminium loses 3 valence electrons because it's from group 3. So it forms Al3 plus ions, right? So potassium and aluminium are examples of metals. So metals in general will lose valence electrons to form positive ions. So this is one good way to tell from a reaction whether something is a metal or not. Metals lose valence electrons and form positive ions. How do you know it's a positive ion? Because there are less electrons than the protons. All right. So this is for metals. We have just covered how metals form ions. How about non-metals? So non-metals, quick example like oxygen. If you were to go to the periodic table, you know that oxygen is a non-metal because it's on the right-hand side of the periodic table, right? However, based on the chemical reactions, how can you tell that oxygen is a non-metal? Not just based on the periodic table, but if you look at the reactions, you have to see whether oxygen tends to lose or gain valence electrons. If you go to the periodic table, you will realize that an oxygen atom of oxygen has 8 electrons. This is because it has 8 protons. Therefore, for the atom, it's also 8 electrons. Remember, atoms are not charged. So the electron and the proton are the same number. So if it's 8 electrons, the electronic configuration of the oxygen atom is 2, 6. Obviously, this is not stable because in the outer shell, it has 6 valence electrons. 6 is not a fully filled outermost electron shell. So what can it do? Will it lose 6 valence electrons? Or is there another way to achieve a fully filled outer electron shell? Remember, outer electron shell to be fully filled means it needs to have 8 because this is the second electron shell. Second shell, maximum 8. Therefore, instead of losing 6, it is easier, probably, to gain 2 valence electrons. And that gives you 2, 8. All right. So oxygen atoms gain 2 valence electrons to form 2, 8. So now you can see the second electron shell, the outer electron shell, which is the second shell, is fully filled with 8 electrons. Now, so at first it had 8 electrons. Now it will have 10 electrons. Reason why does it have 10 is because it has gained 2 valence electrons. But the protons remain unchanged at 8 protons. Remember, protons are never lost and never gained. The number of protons wouldn't change in a chemical reaction. So it's quite obvious now, we have the reverse situation. We have more electrons than protons, right? 10 electrons versus 8 protons, more electrons than protons. Electrons are negatively charged. If you have more electrons, this means that it's a negative ion. And so this ion has a charge of minus. How many minus? How negative is it? It gained 2, so it's 2 minus. So this is called the oxide ion. Okay, so negative ions, the name will change slightly. Okay, oxygen atom, but oxide ion. All right. So how do you draw the oxide ion? Put the symbol in the center as O. 2, 8. However, you need to be extremely careful. The 2 electrons gained must be drawn in a different symbol. Can I please highlight this to you? The 2 electrons gained have to be drawn in a different symbol. And remember to enclose the ion in square brackets with the charge indicated on the top right-hand corner outside the bracket. Okay, so this is the electronic structure of an oxide ion. So oxygen is a typical non-metal. Non-metals gain valence electrons in order to form negative ions with a fully filled outermost electron shell. So how do we explain in words how this works? Again, you have to say oxygen atom has 6 valence electrons and does not have a fully filled outermost electron shell. Okay, so you want to write is 2, 6. We are right. It's a sentence. Okay, so it's 2, 6. The atom is 2, 6. Hence, the oxygen atom gains 2 valence electrons to form O2 minus ions with a fully filled outermost electron shell. Okay. Now, please don't underestimate the importance of writing it out in words, because very often in your O levels, not only must you draw, you must be able to express it in words. Okay, so expressing in words could be a problem, a potential weakness for you. Therefore, it's good to practice now. All right. So this is for oxygen and how it forms the oxide ion. Okay. Now, besides oxygen, of course, you have other non-metals. Okay. So take, for example, you have group 7. If you go to group 7, there's fluorine. Fluorine has 9 electrons in its atom. So it's 2, 7. All right. So you can immediately see again, the outer shell is not fully filled. The outer shell is the second shell and it only has 7 valence electrons. Therefore, this is not a stable atom. All right. So what will the atom do? The atom, in order to achieve a fully filled outermost electron shell, has to gain 1 valence electron. So it becomes 2, 8. So you realize that fluorine, when it gains that valence electron, it becomes 2, 8, just like the oxide ion, right? So this is the F minus ion. Why is it only minus? Because you only gained 1 valence electron. So the charge is 1 minus. And we usually omit the 1 from the formula. Now, just like oxygen just now, oxygen atom became oxide ion. Fluorine atom, when it gains the valence electron, becomes the fluoride ion. All right. So I'm sure you can work out the rule already. If you gain 1 valence electron, your charge is 1 minus. If you gain 2 valence electrons, it'll be 2 minus. If you gain 3 valence electrons, 3 minus. And this is all dependent on the group from which the element comes from. So group 7, fluorine, chlorine, they will form F minus, Cl minus, Br minus, I minus, so on and so forth. So group 7, they will gain 1 valence electron. Group 6, oxygen, sulfur, they will form O2 minus, S2 minus. Group 5, nitrogen, phosphorus, they will form N3 minus, P3 minus. Okay? And with that, we can see the non-metals are the reverse of metals. Non-metals will gain valence electrons to form negative ions with a fully filled outermost electron shell. How many valence electrons are gained depends on the group of the element. So from the group, we can work out what's the charge of the ion. And this is a very important rule to bear in mind. Okay? So before we move on to the last part, which is ionic compounds, how do we draw ionic compounds? Okay, can you please ensure you have copied down these things? And once you have done so, please also give me a thumbs up so that I know you're done. Okay, so now we have learned how metals form ions, non-metals form ions. So the question now is, okay, we know that metals lose valence electrons, non-metals gain valence electrons, right? So what happens when we put a metal and a non-metal together and react them? So take, for example, potassium and oxygen. Potassium loses one valence electron. Where does that one valence electron from potassium go to? Oxygen gains two valence electrons. The two valence electrons came from where? Right? So it's logical. Potassium loses one valence electron. Oxygen gains two valence electrons. This means that potassium is able to transfer its valence electron to oxygen. And that's how the chemical reaction works. The chemical reaction between potassium and oxygen involves potassium losing one valence electron and oxygen gaining the valence electron. All right. And this is what we call a transfer of electrons, which results in the formation of an ionic compound. Why ionic? Because we know that potassium loses electrons from K plus ion. Oxygen gains valence electrons to form oxide ion. So it's ions, therefore it's called ionic compound. All right. So now we're going to go through how do we draw an ionic compound. So take, for example, potassium oxide. Whenever you are given a name, you need to first work out, okay, this is ionic compound. Why is it ionic? It comprises of metal and non-metal. Potassium is a metal, oxygen is a non-metal. So it's an ionic compound. All right. The next thing you need to work out is the formula of the ionic compound. And this is where you must write out the charges first. You cannot assume that it's KO, full stop. In fact, the formula is not KO. The formula doesn't have one potassium, one oxygen. If you were to think in terms of their charges, it is immediately clear why. Potassium forms K plus. Oxygen forms oxide, which is O2 minus. The charges of the positive and negative ions are not balanced. In an ionic compound or in any compound in general, the charges have to be balanced. This is not balanced if you just have one potassium and one oxide. Therefore, we know that you will need to have two potassiums to balance out the doubly negative charge on the oxide ion. Therefore, it's K2O. All right, so the formula must be written out correctly. And to write the formula correctly, you must first write the charges out correctly, which is why just now the rules that you copied down are very, very important. By remembering that potassium is group 1 forms 1 plus, oxygen is group 6, it forms 2 minus, you are able to write the formula K2O out very, very quickly. Now, this is also logical. Potassium loses one valence electron, but oxygen gains two valence electrons, which means that oxygen needs to bond with two potassium because each potassium can only lose one valence electron. So now, how do we draw the dot and cross diagram? We can represent the bonding in an ionic compound using a dot and cross diagram, right? So after you have worked out the formula, you will know, oh, I need to draw 2K plus, 1 O2 minus, right? So to draw the dot and cross diagram correctly, you must decide what goes into the center. The one that goes into the center is the one that is in a smaller amount. K2O, 2 potassiums, 1 oxide. So oxide goes into the center. Whereas the 2 potassium ions will have to go to the sides. Okay. Next, you must work out the electronic configurations. You must either do it in paper on a working, all right? You can do working, but make sure that your final answer is shown clearly. All right. So I advise you, you can do the working maybe on a piece of rough paper, or once you're more familiar, you can just do the working inside your head. Don't need to write out. You must ensure whatever that goes into your answer blank is only the dot and cross diagram, nothing more. All right. This is to avoid ambiguity. All right. So just now we already did this, so I'll just go through it quickly. Potassium is 2881, loses 1 valence electron. So K plus is 288. 2, 8, 8. Okay, so you drew this just now already, 288. That's the K plus ions electronic configuration. Okay, same for the one on the right-hand side, it's also K plus, so it's also 288. And that makes sense because this means it has a fully filled outermost electron shell with 8 electrons in the outer shell, the third shell. Okay, so that's K plus. How about O2 minus? At first it's 2, 6. But now it has gained 2 valence electrons. So this is where you have to remember the 2 electrons gained must be drawn using a different symbol. If you notice, what I have done very intentionally is to make potassium's electrons cross, oxygen's electrons dot. That's why it's called a dot and cross diagram. It is to symbolize that these electrons had come from different atoms, and the 2 electrons gained by oxygen came from potassium originally. Right? So this is the dot and cross diagram for potassium oxide. So revise, the first thing to do is to establish that it's ionic compound because it contains a metal and a non-metal. The second step is to write out the charges, K plus, O2 minus, and work out the formula, is K2O. Do not make any assumptions about the formula. Make sure you write out the charges and work it out. Finally, to draw the dot and cross diagram, we need to know the electronic structure of each ion. So you can do that working inside your head once you're more familiar and ensure that you get the number of electrons correct. Okay? Now, this is a typical ionic compound, potassium oxide. So why is it that the ions are attracted to each other? They must be attracted to each other. If not, how will it bond together, right? Bonding together means that it's attracted to each other. So the K plus ions and the O2 minus ions are attracted to each other. So K plus is attracted to O2 minus. How? This is called a strong electrostatic force of attraction between the oppositely charged ions. All right. So this is a very, very important keyword, strong electrostatic force of attraction. Now, this is a keyword that probably you have been introduced to in Sec 3. You may have forgotten it, but you definitely heard it before. But the idea now is we need to understand what does this thing actually mean. What does electrostatic mean? Now, electrostatic comes from the word electricity, electric, all right? And static. Static means it's not moving, all right? So what it means is positive attracts negative. So in such a situation, the positive ions attract the negative ions. Therefore, it's a strong electrostatic force of attraction between the oppositely charged ions. Now, because it's attracted to each other, many ions, many K plus and O2 minus can attract each other. This forms a massive structure. And this massive structure is called a giant ionic lattice. So ionic compounds have a giant ionic lattice structure, okay, which is formed by many oppositely charged ions attracted to each other by strong electrostatic forces of attraction. Okay. So if you're done with this, copying this, please give me a thumbs up so I know you are done and I can move on to the physical properties of ionic compounds. Very good. Now, once you know the bonding and structure, the bonding is strong electrostatic forces of attraction between oppositely charged ions. The structure is a giant ionic lattice structure. Once you know the bonding and structure, you can easily work out the properties of ionic compounds with such bonding and structure. The first important physical property is that it has a high melting and boiling point. All right. Why? Why will it melt and boil at a very high temperature? Melting and boiling requires forces of attraction to be overcome. To melt something, you need to heat it up because it requires that thermal energy. It must take in that thermal energy to overcome the forces of attraction. So now the idea is we need to think of the forces of attraction. What are the forces of attraction present in ionic compounds? The forces of attraction are the strong electrostatic forces of attraction between the oppositely charged ions. The keyword here is strong, right? So in ionic compounds, there are strong electrostatic forces of attraction between the oppositely charged ions. So stating the forces of attraction is the key to explaining how melting and boiling point will work. Okay? Because we know that melting and boiling involves overcoming forces of attraction. So there are strong electrostatic forces of attraction between oppositely charged ions, which, if it's strong, it will require a lot of energy to overcome. Because it's strong, you need a lot of energy to overcome. Therefore, the melting and boiling point is very high. Okay? So this is an important key idea. Melting and boiling involves overcoming forces of attraction. So because these are strong electrostatic forces of attraction between oppositely charged ions, they will require a lot of energy to overcome. So you will need to heat it up to a very high temperature before we are able to melt the ionic compound. Okay, so this is typically a 2-3 mark explanation question, right? Explain why potassium oxide has a very high melting point. This is the explanation, all right? So being able to have the concept in your head, being able to also have the correct words in your head will be very crucial. Okay, so melting point is the first property. The second property, which is also very important, is electrical conductivity. Does it conduct electricity or not? All right. So as it turns out, ionic compounds with a giant ionic lattice structure, they do not conduct electricity in the solid state. So if it's a solid ionic compound, it will not conduct electricity at all. If you connect it to a battery and a light bulb, the light bulb doesn't light up. because in the solid state, it doesn't conduct electricity, but conducts electricity. It becomes a good conductor of electricity in the molten or aqueous states. Okay, so molten means you melted it, it's a liquid. Aqueous means you dissolved it in water. So if I were to melt or dissolve it in water, it becomes a good conductor of electricity. So potassium oxide, for example, if I were to melt potassium oxide, molten potassium oxide is a very good conductor of electricity. However, if it's in the solid state as a crystal of potassium oxide, it doesn't conduct electricity at all. So what is the idea here? You need to know what is electricity all about. Electricity is about moving charges, particles that are charged that can move. So in the case of ionic compounds, you have ions that are charged. There's positive ion, there's negative ion. These are charged, right? There's positive charge, there's negative charge. The question is, can they move? Because electricity involves moving charges, right? So in the solid state, they don't conduct electricity. Why? Because the ions are held in fixed positions. And why are they held in fixed positions in the solid state? Some force must be holding them together. And the force we have just learned is an important 5-word phrase: strong electrostatic forces of attraction. Okay, the ions are held in fixed positions by strong electrostatic forces of attraction. If they are held in fixed positions, this means that the ions are not free to move. Okay, so in the solid state, the ions are not free to move at all because they are held in fixed positions by the strong electrostatic forces of attraction. So what's the difference between the solid state and the molten and aqueous states? In the molten and aqueous states, the strong electrostatic forces of attraction between the oppositely charged ions have been overcome. When we melt something, you heated it up. By heating it up, you have already overcome these strong electrostatic forces of attraction. So when you overcome the forces, the particles, in this case, the ions, are free to move, to conduct electricity. Okay, so it looks like a lot of words, but the concept here is electricity. Electricity is about moving charge. So the question is, can the charged ions move freely or not? Okay, so let's take this down. And once you have taken this down, please give me a thumbs up. Okay, and also ask if you have any questions. Okay, now these are the two main physical properties of ionic compounds. Ionic compounds generally have high melting and boiling points. And the reason is there because there are strong electrostatic forces of attraction between oppositely charged ions, which require a lot of energy to overcome. The second physical property is that ionic compounds do not conduct electricity in the solid state, but will conduct electricity very well in the molten and aqueous states. Like I said again, electricity is all about moving charges. So you got to think, are the ions which are charged free to move or not free to move? All right. These are the two main physical properties of ionic compounds that you must be able to explain. All right. And this accounts for a large proportion of the marks in a chemical bonding question. So it's crucial that you learn this. Even after you have copied this down today, you go back and you think through it and you learn the phrasing. Learn to understand the concept. Don't just memorize the words. You must know why. Why do we use these words? What do these words mean? All right. Now, there's one last physical property, but you don't have to explain this. You just need to know it. Is that ionic compounds generally are soluble in water, meaning generally most ionic compounds can dissolve in water. Okay, generally. This means that there are some exceptions. However, most ionic compounds are soluble in water. This is in water. Now, what is the opposite of water? The opposite of water will be something like oil. Ionic compounds are insoluble in oil. Oil is considered an organic solvent. So you cannot dissolve ionic compounds in organic solvents like oil, all right? Because ionic compounds are insoluble. Okay. Now, this really concludes ions, ionic bonding, including how to draw the dot and cross diagrams for ionic compounds and the physical properties of ionic compounds. Now, with this, you have really finished half of chapter 6, chemical bonding. So thus far, for the past 2 lessons, we have really gone through the whole of chapter 5, atomic structure, and half of chapter 6, chemical bonding. So the next session, right, we will finish with covalent bonding, and we would really have finished the whole chemical bonding. Okay. Now, I know that we have not gone through the questions in JH2 today, but I will leave them for the next time because I think they require some time to explain. However, based on whatever we have learned today, you would have learned enough to cope and tackle the questions in JH1 and JH2. So can I advise and encourage you to try out some of these questions in your free time to ensure that you have internalized the concepts that have been taught. All right. So with that, that concludes ionic bonding and ionic compounds. All right. So we have really finished chapter 5 and half of chapter 6. For the next lesson, we will finish chapter 6 with covalent bonding, which occurs between two nonmetals. All right. So thank you, and I hope to see you next session.